Hello, my name is Diogo Carvalho and I'm a master student at IST. In this video, I'll briefly explain to you the ideas behind my master thesis entitled Plasma Tomography using Tikhonov Regularization. Let us start with the first word in the title. What exactly is a plasma? When you take a gas and you inject energy into it, electrons start being removed from their atoms. This creates a mixture of free electrons, positive ions, and possibly still some neutrals. This mixture is exactly what we call plasma, also known as the fourth state of matter. The sun you see every day in the sky is an example of it, and people nowadays are trying to mimic one here on Earth to produce energy. Some of these experiments are performed in donut-shaped devices called tokamaks, where the plasma is confined inside vacuum chambers, very well isolated from the outside. To understand the complicated phenomena that happen inside them, we need to use diagnostic techniques, and plasma tomography is one of them. Computed tomography was first proposed as a medical imaging technique algorithm in the 60s by Alan Cormack. For this development, he was awarded, together with Godfrey Hounsfield, the Nobel Prize of Medicine in 1979. By exposing people to X-rays and collecting the transmitted radiation, they made it possible to reconstruct cross-sections of the human body without the need to cut anyone open. This technique, with some modifications, was later applied to a broad range of fields, being plasma physics one of them. In plasma tomography, instead of injecting X-rays, the plasma itself is the source of radiation. This radiation has different origins. For example, line radiation is associated with the de-excitations of electrons from higher to lower energy orbitals. Bremsstrahlung radiation, translated as braking radiation, is associated with the decelerations of electrons when passing near a positive ion. The sum of all these contributions generates a spectrum that passes through the plasma and can be measured from the outside using bolometers. These bolometers will determine the power radiated along a given line of sight. Just like in medicine, by using multiple lines of sight at different positions, we can reconstruct a pixelated image from a cross-section of the plasma, thus obtaining information about its temperature, density, among other quantities. The main difficulty is the number of lines of sight available. While in medical applications there are thousands of them, in plasma tomography we normally use about 50 lines of sight. Now, let us see an example of how this reconstruction is done. For simplicity, imagine a 2x2 grid representing our plasma, with some general values A, B, C, D equal to the power that each pixel radiates. One bolometer, let us name it B1, will measure the radiation along a certain line of sight. In the simplest case, we can say the value B1 measures is equal to the sum of the pixel values which its line crosses, meaning A plus C. To fully determine the values of A, B, C, and D, we need to have an equal number of bolometers, in this case 4, and each detector must cross a different combination of pixels. For example, we can define B2, B3, and B4. If we do this, the problem becomes just an inversion of a system of equations, which is easily solvable. But what happens if this is not possible? Can you correctly determine the values of 4 pixels with just one bolometer? For example, B1? The answer is no, you can't, since there are in fact infinite solutions. So, how do we find the best one? This is exactly where Tikhonov regularization enters. We might say that we want the solution to be smooth, meaning neighboring pixels should have similar values. Also, physically, it makes no sense for pixels to have negative values and for radiation to come from outside the vacuum chamber. Tikhonov regularization will then use this a priori knowledge to find the solution that best balances this info and the measurements from the bolometers. It is, of course, necessary to understand which conditions are valid and how to balance them. Also, this type of algorithms, not in a 2x2 grid, but imagine a case where we have 200 by 200 pixels, take a long time to converge for a solution, making it very time-consuming to generate all the reconstructions necessary for research purposes. In my master thesis, I will then try to implement a tomographic algorithm based on Tikhonov regularization that can speed up the reconstruction process while still providing sensible results. I'll be using the existing JET tomographic database, but the goal is to obtain a method general enough so it can also be applied to other devices. This work will be performed at IPFN under the supervision of Professor Diogo Ribeiro and Professor Horácio Fernandes.